Now it should be recording. And then I'm going to share my desktop, which is this here, so that whatever I do on my computer will be seen by whoever on the other side. And they don't need to see my email though. Okay. So let's look at our agenda for today. No, if I turn that speaker on, you will hear it through the computer. But since you're here, you don't need to hear me. So because I have about 20 students or online students, some of them will be participating in the class synchronously while we're doing this. Yes. And also I'm recording everything, so everything that we do here, everything that I'll try not to use the board so that the online people can see what we're doing. Everything will be recorded, so you'll get a chance to review everything. So during the lecture, I would rather you focus on understanding what we're talking about rather than practically trying to keep up with the notes. But I know some students who learn from taking notes, so I wouldn't discourage you from taking notes if you want to take notes. Okay? So administrative stuff, we did that. We did the name game successfully. Let's look at our syllabus. Who didn't get a copy of the syllabus? John? Okay. Oops, it's the wrong class. Let me open the right one. Engineering 230, 2030. Where's the syllabus? You knew John before? Yeah. Oh, how unlucky. Okay, this is Engineering 230, which is statics or engineering statics, and I'm your instructor, Dr. Enriquez. Most students call me Dr. E. I'm still trying to investigate. There's rumor that E stands for evil. I thought it was E for excellent, but we will see. Thank you. It's easy to get a hold of me by email. Most students think of it as texting or instant messaging, because if I don't reply to your email unless I'm lecturing or I'm in a meeting or I'm dead, if I don't respond within 15 minutes, something must be going on. So, I'm almost never in my office. That's why I cannot pick up the phone. If you leave a message, I will get it in my computer and call you back. So let's see. I have office hours. Oh, right before class, 1 to 2, and right after my circuits class, 5 to 6. Oops, this is not quite right. Oh yeah, and in the Learning Center on Tuesday afternoons, and also online office hours on Sunday evenings. Yes, 7 to 8 p.m. on Sunday. I've found that it's the most popular time for office hours because students don't really think about their school week until Sunday evening. So what I wanted, this Sunday is a holiday. Monday is a holiday, so I'm gonna move the first online office hours to a Monday evening. That makes a lot more sense rather than having it Sunday night, knowing that Monday is a holiday. You all know that Monday is a holiday, right? It's kind of weird that we start a week before Martin Luther King only to have another long weekend. Anyway, so I will hold the first online office hours on Monday evening next week. And my suggestion is to just try and see how it works, just in case, eventually you have say we have a test on Monday and you're panicking Sunday evening. At least you know how to participate in the online office hours. And most students really just log in and kind of lurk in the background. They don't really have a lot of questions because they probably haven't even started the homework. They're just asking for other students to ask good questions, so that's a good way to get started on your homework. We meet from 2:15 to 3:35 Mondays and Wednesdays in this room, and this is a 3-unit class. It says here that the prerequisites are Math 251 or 241 and Physics 250. The Math 51, Math 251 or 241 are crucial, are critical. You need to be able to find simple derivatives and simple integrals. Okay, simple integrals are integrals of polynomial functions. Okay, and if you're taking Calc 2 right now, that's fine. By the time we need trigonometric substitution, all those more elaborate techniques of integration, you would be at that topic in your Calc 2. Okay, Physics 250 is a prerequisite, but from my experience, there's really no correlation between success in Physics 250 and success in this class. In fact, a lot of students find this class easier than Physics 250. I will show you in a minute why. For one thing, the coverage of this class is like probably one chapter in Physics 250. Right? Remember, you did equilibrium problems, statics, probably called statics or equilibrium in one chapter in Physics 2. That's all we're going to talk about. Okay. So in terms of the coverage, there's really not a lot of new concepts you're going to learn in this class. Instead, we're going to try and apply what you've learned or what you supposedly have learned in Physics 250 and apply them to engineering problems. Okay. The textbook is the 9th edition. I was trying to switch to the 10th edition. They didn't send me a copy of the textbook, so I didn't. I'm not sure what the copy is, what they're selling in the bookstore. It's the 9th edition, so that's good. However, if you don't have a textbook yet, my suggestion, I shouldn't be recording this. The bookstore people are not going to be happy, but they probably won't. Don't tell anyone, okay? I'm going to get in trouble. My suggestion is for you to go online and look for, say, a 3rd or 4th or 5th or 6th edition of this textbook. I mean, statics, mechanics has been mechanics since a long time ago. So, and the thing is, I actually post the homework problems on our website. So those are the only things that they changed. They changed the numbers, the order of the problems, and they have a new edition. And how much is the textbook in the? Oh, really? That's not bad. That's not bad. $40. But you can probably get them $5. You know, an old edition online. Anyway, I'm glad they didn't switch to the new edition. Go ahead. I didn't hear that. Okay. Yes. You can purchase that, or you can be friends with someone else. You shouldn't do that. That's not. You're violating copyright rules. Okay. Let's see. Here are the student learning outcomes. Okay, these are the things that the students who complete this class will be expected to be able to do efficiently, hopefully. Okay. Attendance is not required. However, okay, if you miss more than 6 hours of absence, so that will be about 4 meetings. Okay, I have the right to drop you from this. I'm going to turn this off because I can't really see my screen very well. But it's really your responsibility to drop the class if you want to drop the class, to officially withdraw. Okay. We are supposed to have hours by arrangement for this class. Hours by arrangement, basically for every week, you're required to log in for this class, like the same way you log in the Learning Center. Just make sure that you do Engineering 230. But the hours by arrangement work will be homework that will be submitted weekly down here. Okay, and also the hours by arrangement can also be fulfilled by attending. The STEM Center is going to have a speaker series on Wednesdays 5 to 6 starting January 30th. So you need to attend those. I think many of your other classes will probably require you to attend it to support them. Okay. Work will be done on 8.5 by 11 paper. Okay. using the following required. This is the first. I'm happy finally got to change this. The first time that I've changed this to required homework format. It used to be suggested and nobody followed it. Yes.
So if there's any one of the presentations that count for 4 HPA hours, or do you have to go to 4?
No, it's 1 hour. The presentation is 1 hour, so it's 1 hour. It's really presentations for your benefit. So my suggestion is look at the topics. I will post the topics if it's something that you're interested in. It's something about engineering, then definitely go. Okay, I think they're also giving snacks. So I'll be there. Okay. Look at that format carefully. Okay, and try to follow that. Otherwise, I will return your work. Okay. It really helps me grade much more easily, and it will help you when you're reviewing for the test. I also will devote 2 hours a week just to answer homework problems on Tuesday afternoons, 4 to 6 p.m. in the Mesa Center. Everyone knows where the Mesa Center is here? STEM Center? Okay. We're going to have quizzes, which may or may not be announced. And if we have quizzes, it will be at the beginning of the class. The unannounced quizzes will be given if a lot of people are late. You know. It hasn't happened in 4 or 5 years that I gave a surprise quiz. But if half of you are not here, because I don't want to start the lecture if only 2 people are here, and then people are going to be asking me to repeat everything. Instead, I'm going to give a quiz. Okay, so as long as you show up on time, we shouldn't have any problems about surprise quizzes. Their quizzes are done online, and their quizzes will be different. The test will be the same, but the quizzes will be different. I think the quizzes will be more difficult. I guess it will be timed. They have exactly 30 minutes. Most of them panic. There's a timer right in front of you while you're doing the quiz. Okay. Of course, the online people don't have surprise quizzes. They're not supposed to come here anyway. Okay. Tests. There will be 4 1-hour tests. It should be an hour and a half. Okay. And they will be announced in advance. It should show in our course outline the approximate timing of the test. So after the 4th week, we're going to have our first test, and then we're going to have another test on the 8th week. So there will be 4 tests kind of all throughout the semester. And the 4 tests, on average, will account for 60% of your semester grade. Makeup tests will not be given unless prior arrangements are made, and it has to be a valid reason. And prior doesn't mean you're going to send me an email at 1:59 p.m. saying, "Oh, I'm at the doctor's office because I'm sick," or give me a call and say, "Dr. Ian, I'm sick today. I can make it to the test." Final exam is 25%. And if you look at this one here, if your class grade, okay, which is the composite of your HBA, which will be your hours by arrangement assignments, quizzes, and tests, okay, before the final exam, you have a 93% or better, you're exempted from taking the in-class final. So giving you a chance to study more for your other classes. On the average, I'd say between 20 to 40% of the class every year here don't have to take the final exam. Okay, but it says here each test should be 80% or higher. So you cannot have 100, 100, 100, and then a 79. Although the average of those 4 will be over 93. I want to make sure that you learn everything in the class. Okay? Any questions? So after today's class, you should be ready to start working on the first homework set. And the first homework set is do. Let's look at web access. Are you guys familiar with web access? Do you know how to access web access? Okay, so if you go to MRooms, okay, all the class materials will be here. Let's see. Is this the right class? Yeah, it's engineering. This is 260. Engineering 230. Okay. So if you log into it's smccd.mrooms.net, you all know how to get into this. Yes? Okay, if you don't, your username is your G number, right? And your password would be your date of birth, right? Month, day, year. So let's see, this is what you're going to see. This is what I see, which will be slightly different from what you'll see. I'll pretend that I'm a student. Hi, I'm a student, a temporary student. This is what you're going to see. So everything I give you in class will be here. So for instance, if you lose a copy of your syllabus, you can just download it here. Okay. And in addition to that, we have resources that are applicable. So anything that's above, I've organized it according to topics. Topic 1 up to topic 16. Okay. Currently only topics 1 to 3. Okay. So approximately one topic is about 1 week. Okay. And everything that pertains to the whole semester will be uploaded up here above the first topic. Okay, so for instance, our syllabus is up here. You can check your grades online by clicking here. It will go to this link. Okay, and if you registered before, I think it was January 7th when I did it, you should be able to do this, check your grades online. Of course, it would say empty, but at least it's there. When you're checking your grades online, I want you to do that every week because sometimes I forget to record your scores for the homework. You know, there'll be one homework per week. So, and I try to. It's very rare that I don't hand the homework back the next class. So I want you to check your grades online every week to make sure that I gave you the grade that you deserve. So sometimes I skip the grade, and sometimes I give somebody else's grade to you. So if it's less than what you deserve, let me know. If it's more than what you deserve, it's up to you. Yes. If we go back to our web access, it says here, okay, homework number 1 is due Wednesday the 23rd. Okay, so the homework due dates will be here on our calendar. So this area here you should pay attention to because this is where the upcoming events are. Any important announcements, for instance, maybe scholarship opportunities, maybe internship opportunities, deadlines, you know, you might find in the news forum or our calendar. I might just send it to you by email. Part of your assignment, I want you to complete the first day survey. So when you get home, just click on this link. Okay, it takes you to an online survey. Oops. I should open that survey. I'll do that tonight. So but it's just a series of questions about you, what your background is, what your major is, what grade you got in physics if you've taken physics, you know, things like that. Hi, Nico. No. Hi, Victor. Here's a copy of the syllabus. And your assignment is for you to know the names of everyone here by next time, okay? Okay. In addition to that, if you are unable to come to class, okay, say you're sick at home, you can still attend class virtually. If you click on this link here, okay, this is you confer lecture. If you click here, you will see, oh, there's a link here for students. You click on go, and we'll ask you to log in, and then you're going to connect to me, and you'll see everything that I'm doing. Okay? So Where were we? We're over. Oops. Over. What happened? Okay, so I was over here. I need to go back there. And then go back again to web access. Okay, there we go. So that's how you're going to connect to the live class if you're not here. You can also connect to the online office hours on Sunday. So if you click on this link here, okay, the passcode is over here. If you want to use your phone, you can use your phone. Most students just use their computers. They just listen to me, and there's a chat area where they type their questions. I don't know, maybe they don't want to use their cell phone minutes. That's why I don't want to call. I also archive all the lectures during the semester, as I mentioned earlier. So if you look at this link here, this is the link of all the archived lectures from last year. So after tonight, this link is going to change to the archived lectures for this semester. Okay, so if you look at this, if you want to get ahead, listen to all these lectures for the whole semester last year, and then you let me know next week. I'm ready to take the final exam. I'll give you the final exam. Okay, so for this will be available starting. It will still be available until tonight. As soon as we have our first lecture, I'm going to update it. But if you want this as a resource, you might want to click on it tonight before I change it, and then just bookmark it. It would still be online, but it will not be available on our website. Where were we? Same thing with Sunday office hours. Okay, all Sunday online office hours are archived. So this is tabulation of the hours last week. So as you can see, these are the number of students who attended the online office hours. Sometimes we have 10, sometimes we have 3, 10, 13, and there's always 1 or 2 students that show up every Sunday. That's part of it. And I also have included some links that I think might be useful. So some resources for reviewing math and physics, resources for reviewing vector arithmetic, and so on and so forth. Remember how I told you can purchase an older edition of the textbooks, and the reason is because for the homework problems, I actually upload the actual homework. So what you can do is just print this and then put your solution here. So even if your version of the textbook is wrong, but the textbook we're using is really, really old. The original author is actually dead now. So, but they're still using his name as the first author. I used the same exact book. When was that? Maybe 30-something years ago, at least. Okay. It's one of the most popular textbooks. Let's see. Not only do I upload the PDF files for the actual homework problems, I also photocopied the back of the textbook to give you the answers that are available. So you just really no need to have the latest edition of the text. It's a big file, but yeah, I just photocopied it and uploaded it. But I cannot guarantee that the answers are correct. In fact, some of them are wrong. Okay? Any questions about the class in web access, connecting to the class online? No? Okay, so I'm ready to start doing my job, which is talk about statics. So we have about 45 minutes, okay? So we're going to do a short lecture, and I was planning to do the first day survey towards the last 10 minutes of the class, but we can't because there's actually a graphics class going on next door. So you just have to do that on your own as part of your homework. Let's see. Um, if somebody has a computer, if you can log in as I'm lecturing, that's actually nice, because sometimes I don't realize that I get kicked out of the internet and I continue lecturing when in fact it wasn't receiving on the other end. But maybe eventually. You know how unreliable things may be. Okay, this class is statics of rigid bodies. Okay, so we're going to define each of those words, what's statics, what's a rigid body, in the context of what we're going to learn here. Statics is really one of the main areas of this branch of study called mechanics. Okay, which is really, physics 250 is actually mechanics. Right? That's what you studied in physics. Physics 250, we have taken physics 250. Physics is traditionally, at least college physics, is traditionally divided into three parts. For us, it's 250, 260, 270. 250 is mechanics, 260 is electricity and magnetism, and 270 is everything else that's left out. So it's like a combination of whatever. And it depends on the textbook that you're using. It depends on the teacher how it's divided. So by the way, if you're taking physics from different institutions, that's not a very good idea, because even if it's within the same district, okay, if they're using different textbooks and the teachers are dividing the topics differently, you run the risk of missing some important topics. Okay, so there's no reason to go to other physics teachers. We have very, very good physics teachers here, from what some of them are very good. Okay, so mechanics deals with the state of rest or motion. Okay, so the object or body is either at rest or in motion, and we're trying to describe the state of rest or motion of these bodies as acted upon by forces. Okay, so the main things that we're going to study in mechanics are forces. We have an understanding of what a force is, right? Hopefully. Yes? Okay. So we're going to formally define what a force is later on, but you should have an idea of what a force is, right? Yes? Okay. Okay. And bodies that are receiving these forces, whether they're resting or in motion. Now, depending on whether they're at rest or moving, okay, mechanics can be divided into two parts. First part is statics, okay, when the object that is under the action of forces that you're analyzing is either at rest or moving with a constant velocity. Okay, so if the object is not moving, or the object is moving with a constant velocity, and even if it's under the action of forces, okay, then we are studying what's called statics. Okay. On the other hand, if the object is moving, you're studying dynamics. Okay. In physics 250, you actually studied both statics and dynamics, and I don't necessarily remember if you probably didn't go through statics first and then dynamics. Am I correct? I think the first topic you did in physics 250 was kinematics, right? Which is really motion, right? Which is really under dynamics, right? If you look at it, strictly speaking, statics really is just a subset of dynamics, right? Because here's bodies in motion, okay? Here's bodies moving, but with constant velocity. Right? Okay. So luckily for us in this class, we're gonna focus on this. And of course, if you remember physics 250, okay, the things that got really hairy were things that were related to angular momentum, rotation, things like that. We're not gonna do any of those. Okay, as I mentioned earlier, it's really just one chapter of your physics 250 class. So you should be excited that this should not be very difficult. Now, we can classify mechanics, okay, as we have done up here, based on the state of rest or motion of the object. If it's not moving or moving with a constant velocity, it's statics. If it's moving, it's dynamics. Okay, but we can also classify mechanics based on what I'm calling the properties of bodies. Okay, what do we mean by property? Some objects are particles. What do I mean by a particle? What can you say about an object that can be described as a particle? Parts of an object. So is this, whatever this I'm holding, is this a particle? I'm talking about this one. Is it a particle? Okay, so give me an example of a particle then. Okay, so he says something about a point. Okay, and mathematically, a point has no length, no width, no thickness, no height, right? So this is dimensionless, right? So when you say about a particle, something that's tiny, right? Okay, so strictly speaking, a particle is something that has no dimensions. Of course, that's impractical, right? There's really nothing, okay, that is of no, even an atom actually has a dimension. Even an electron, how tiny it is, okay, still has dimension. Even this box, sometimes I can actually look at it as a particle. This desk can be looked at as a particle. It depends on, so it's not just, although strictly speaking, it has to be something that has no dimension, okay, okay. An object being reasonable to be considered a particle does not just depend on its dimension. The Earth, for instance, can be considered as a particle. Now, let's look at this notebook. I'm changing to the notebook because I don't really know how to describe this to the online people. Here's my notebook. Okay, let's say I'm looking at the kinematics, or I'm following the motion of this notebook. Okay, if the notebook is doing something like this, which it just moved to the right, for me it's to the right, so it moved like this, and during its motion, it just moved horizontally. It didn't rotate, okay? Even though this notebook is strictly speaking not a particle, okay? Because it's not dimensionless. However, if I look at the displacement of this, where's the displacement of this? This corner here actually moved by that much. This corner here moved that by that much. The other corner here moved by the same amount, right? So as long as this object is moving such that the motion of one particle is exactly the same as the motion of the other particles, meaning it doesn't rotate, right? I can get away with looking at it as a particle. In fact, you did that a lot in physics. Instead of looking at this corner of the notebook or this corner of this notebook or this, right? As long as it's in what we call translational motion, the displacement, velocity, and acceleration of any point in the notebook is exactly the same as the displacement, velocity, and acceleration of any other point in the notebook, right? Because it just moved to the left by 2 feet. Whether you're talking about this one, they all move to the left by 2 feet, right? So there's no point in looking at the motion of each particle here because the motion of all the particles are exactly the same, right? So what we did in physics is we focused on one particular particle in the notebook. Which particle is that of the notebook? That is the center of mass, right? So what we did was we'll describe the motion of the center of mass. The center of mass moved to the right by 2 meters, or in your case, to the left, right? And we'll say the same thing happened to the rest of the notebook. Okay, we're able to analyze it as a point by sort of pretending that the entire mass of this notebook that's not dimensionless is really focused on that single point called the central mass. Okay, of course it's an idealization. Another property or classification, property of a body that leads to a classification in mechanics is what we call rigid bodies. When do we say that a body is rigid? John probably has an idea. What do I mean when I say an object is rigid or a body is rigid? Okay, it does not change its shape, so does not How about deform? Everyone okay with the word deform? Under the action of forces, under the action of its motion, okay, it doesn't deform. So for instance, is this box rigid? Probably, right? Is my notebook rigid? It could be looked at, okay. Is this paper rigid? No. Okay, so John is saying that if I hold a piece of paper like this, he's saying that it's not rigid. Why? Okay, because I can bend it. My answer is, well, it really depends. Okay, so if I take that paper, okay, and say pull both sides with a pair of forces that's magnitude 1 pound here and 1 pound here. Okay, so I'm trying to extend it 1 pound. Is it rigid? Yes, right? It doesn't deform. Okay, if I keep increasing the 1 pound and if I'm strong enough, there will come a point when what? It might even rip. Right? So obviously the rigidity of the body is not just a function of the body itself. It's a function of how big the forces are that you're applying. The bigger the forces are, the higher the chances are that it's going to deform, therefore it's not rigid anymore. Okay? So the rigidity of a body is not just a property of the body. It also depends on the forces that you apply, obviously on the magnitude, but it also depends on the manner of application of the forces. So if I take the same piece of paper here and I'll take the same the pair of forces, instead of taking the 1 pound here on the left side to the left, I'm going to take the 1 pound to the left on the right and the other 1 pound here. So instead of trying to stretch it, I'm trying to compress. So what do you say? Obviously, it's not rigid anymore, right? So what we learned here is, okay, the rigidity of this paper is not just a property of the paper, right? It's a property of the magnitude of the forces, right? 1 pound versus 10,000 pounds, it might rip. And it's not just a property of the magnitude of the forces, also it's a property of the manner you apply the forces, right? So 1 pound tensile or stretching, it's okay. 1 pound compressive, it's not. Okay? But at least we understand what it means to assume that a body is rigid. Luckily for us, okay, if you pay attention closely here, in this class, we're only going to be focusing on rigid bodies. Okay? Which means that, what? We're going to assume that under the action of forces, whether it's moving or not, okay, we're going to neglect the deformation or the change in shape of the object. Okay? Now, a third classification of bodies will be those that are deformable under the action of forces. Right? By the way, this first 2 parts here are the only 2 parts that will be considered here in this class, Engineering 230. Everything beyond this will be in a subsequent class. So for instance, in analyzing deformable bodies, we're not going to do it here. You're going to do it in a subsequent upper division class depending on where you transfer. And the class is either called solid mechanics or sometimes called strength of materials, or sometimes it's also called mechanics of solids, which is the same as solid mechanics. Okay, and traditionally this is upper division. If you're transferring to Berkeley, what they've done is they've actually eliminated their statics class. They absorbed the statics class into their strength of materials class, and they moved it down to lower division. So if you're thinking of transferring to Berkeley, it might say that statics is not required. I still would suggest that you take statics because they would actually go through strength of materials as maybe 60% of the class and 40% will be statics. So everything's going to go really fast. In Southern California, they still have statics and strength of materials, but some of them have both at lower division. For instance, Cal Poly San Luis Obispo has strength of materials at lower division. We haven't started offering strength of materials here at Kenyatta because we're not going to have enough enrollment. So in the future, hopefully, we can. Huh? Correct. Yeah, because it's lower division for some universities. So, like dynamics we teach here, although it's upper division for most UCs and for San Jose State. But it's lower division for San Francisco State, Cal Poly, and UCLA, a lot of the UCs in the South. So it's weird. The universities in Southern California have different curriculum compared to what we have here. So if you can have enough students I'd be happy to teach it. It's a really good class. And of course, the extreme case of an object being deformable. What object is extremely deformable? A liquid or a fluid, right? So for civil engineers and mechanical engineers, you will also take an upper division class in fluid mechanics. We are also going to look at some idealizations in this class. You already saw some of them. Okay, a particle is a point mass with no dimensions. It's an idealization, right? But as we saw earlier, depending on what the object is doing, it's perfectly fine to assume the object to be a single particle, especially if what's happening to one particle in the object is exactly the same as what's happening to the other particle. Okay. Again, this concept of rigid body is another idealization, right? Because there's no such thing as a perfectly rigid body, right? But as long as it doesn't deform considerably such that the physics of the problem is changed due to deformation, we can assume that they are perfectly rigid under the action of forces. Of course, this has limitations. Another set of idealizations would be with respect to the forces that we apply. Okay, so for instance, if I say, I'm pushing this table with my finger, okay, with a 1 pound force. If you do a free body diagram of the table, you'll probably show a single arrow, right, acting on a single point on the table. That's an idealization because in reality, there's a finite area of contact between my finger and the table. So the 1 pound force is really not acting at a single point. It's actually distributed over an area. Right? Even your weight is an idealization. Your weight may not be ideal for you, but showing it as a single force, in my case, 161, right in the center, that's an idealization because the weight is really not just acting on a single point. It's acting on every single molecule of my body. Right? So when we draw the free body diagram of a person with a single force there, with a weight, that's an idealization. Okay. Because the force is not acting at a single point, it's actually distributed over a volume. Another idealization is frictionless surface. Okay. It's perfectly smooth. There's no friction. Of course, that doesn't exist. Okay, but we will relax this idealization when we get to chapter, I think chapter 9 is friction. So for the first 8 chapters, we're going to assume that there's no friction. Okay. Just a review of the units, the quantities and physical quantities and their units that we'll be dealing with in this class. Let me know if there's anything that you don't recognize. Length, we're going to use L for length, sometimes R for radius, or D for distance or diameter. And unfortunately for mechanics, okay, we're going to switch from SI, which is System International, I think, or International System, that's based on meters, to sometimes the U.S. customary unit, which is based on feet and, pounds, because we still pump our gas in gallons rather than liters, right? which is unfortunate. So, but you have to know this because you've heard of design flaws because somebody forgot to convert from one unit to the other, right? You've heard of that, right? NASA launches that were unsuccessful because somebody didn't convert units correctly. Mass, we're going to use M for the symbol for variable mass in kilograms in the SI. And are you familiar with the slug? Okay, the slug is really a simple way of dealing with mass in the U.S. customary unit. You know, pounds, right? When you weigh yourself in the morning, okay, it says in pounds. Pounds is really a unit of force, right? Okay, it's not a unit of mass. Okay, if you sort of look at this simple equation, F equals ma. You're familiar with that, right? That's the Newton's second law of motion, right? The force in pounds, this is in pounds, right? Is equal to mass times acceleration. What are the units of acceleration in the U.S. customary system? Feet per second squared, okay? And the unit of mass will be a slug. So really, if the definition of a slug is as follows. If I take a mass of one slug, however big that is, and I apply a force of 1 pound, okay, that object is going to accelerate at a rate of 1 foot per second squared. Okay? So that's the problem with the U.S. customary units is everything is in pounds. Okay, and chemistry even makes it even more complicated. They have something called a pound mass and a pound force. Do they still do that in chemistry? Huh? Oh, you use SI units now in chemistry. That's good. However, when you get your, if you get your solution published still in gallons, which is not in. So they don't use pound mass and pound force in chemistry anymore. Good for them. So everything is SI now. Okay, that's good, but kind of dangerous, you know, because what if you have something in pounds? Anyway. So basically, that's the definition of a slug. It's the amount of mass such that if I apply a force of 1 pound, that mass is going to accelerate by 1 foot per second. So the same way with the definition of a Newton in the force. If I take a mass of 1 kilogram and I apply a force of 1 Newton, that mass is going to accelerate 1 meter per second squared. Okay, so 1 is to 1. Of course, there are other physical quantities, but they're not. These are the main quantities that we'll be looking at in this class. Oops, sorry. And also, these are other quantities and their units that we look at here in this class. Area, volume, acceleration. Okay, fundamental concepts. If I ask your Physics 250 teacher here, invite it. Who is your teacher in Physics 250? Partland. Okay, and I ask Dr. Partland. Oh, Dr. Partland, Victor is going to try to impress you with the knowledge of Physics 250. So what would be, say you have 15 minutes to impress him that you've learned something in Physics 250. What would be those things? Huh? You don't remember anything? Oh, so maybe we should invite him. So I'm trying to ask you, what are the most important things that you learned in physics? Assuming that you did learn something. Hmm? Newton's laws? Okay, good, right? What are the Newton's laws? Newton's laws of motion. How many are there? 3. Okay, what's the first one? Is someone a ventriloquist? I hear a voice, but I don't see. Is that you, Omar?
Yeah.
Okay. What's the first law?
If the body's moving, it keeps on moving, and
At rest, it, okay. Unless, okay, so basically it's saying that if an object at rest will remain at rest or continue moving at the same velocity unless acted upon by an external force, right? So if there's no force applied, okay, it will either remain at rest or continue moving with the same velocity. So the key is it has to continue moving with the same velocity, okay? So basically this is a consequence of what? If the net force is, if the net force is 0, what does it mean to stay at rest or move with the same velocity? The acceleration is 0, basically, right? If it's at rest, the velocity will not change. If it's moving, the velocity will continue to be the same, right? And what's the second law? F equals ma. How does it say? If a particle this time has a net non-zero applied force, so here if the force is not equal to 0, that force is going to what? Result in an acceleration that's proportional to the force. Meaning the bigger the force is, the bigger the acceleration. Okay? And the constant proportionality is the mass. Okay? Oh, by the way, this part here is really just statics. Remember, statics is the study of the state of rest or motion of objects that are either at rest or moving with a constant velocity. Right? What is the third law of motion? Okay, third law is for every force of action, there's an opposite and equal reaction. Okay, so this is also this third law of motion, it applies to objects that are either at rest or moving. So what this tells us is that forces always come in pairs. Did you hear what I just said? So if there's a force cannot exist by itself, there's always another force that is associated with it. In the same way, a force is always an issue between two objects, because a force needs to have an object exerting the force and an object receiving the force. Okay? And the force exerted by 1 on 2 is the same magnitude and opposite sense as the force exerted by 2 on 1. That's basically what action and reaction is. Okay. Other than Newton's laws of motion, anything else that you want to impress Dr. Portland with? Anything else that you learned from physics? That's it? For a whole semester? Anything else? Oh, it's right here. So the F net is really just the vector summation of forces, right? If there's more than one force acting, if the summation of forces is 0, we're still under first law. Anything else? How to draw, very good. How to draw free body diagrams, okay? But that's really not what I'm looking for right now, but that's a good idea. What is a free body diagram? You've heard of a free body diagram, right? What is it really? Okay. Why do you think we draw free body diagrams? Because the teacher told us to. So why would you want to do that? Okay, so it's really that. Oh, That's a really good, clear concept. It's really, a free body diagram is really nothing but a tool in order for you to more clearly and efficiently do this, do the summation of forces. Okay, see her. Okay. Not your physics teacher. Oh, you're teaching physics, isn't it? So really, the free body diagram is just a tool. Our life would have just been fine without free body diagram. It's really because the teacher doesn't, physics teachers and mechanics teachers do not trust the students that they will be able to apply first law, second law, and third law without making it some kind of a graphical representation. It's really a graphical representation to help you apply this law. Okay? So although it's useful, it's really still under this too. You create a free body diagram in order to make sure that if the summation of forces is 0, it's under first law. If the summation of force is not 0, it's under second. I was looking for something else that's also related to Newton. The what? Gravity. Oh, what about it? Does this look familiar? Newton's universal law of gravitation. What does that say? Is it constant? What is constant about this? Huh? What does this say? Newton's law of gravitation. Let me see if I have space here. Does that look familiar? Okay. So what that tells us is, it's called universal. Why is it called universal? Okay, it works for everything in the universe. Okay, so in fact, the Newton's universal law of gravitation says that for any pair of masses anywhere in the universe, M1 and M2, so I have two masses. They are located somewhere in the universe. Maybe near the Earth, maybe out in outer space, but there exist two masses, M1 and M2. According to Newton's universal law of gravitation, what? What does it say? Okay, if these two masses are separated by a distance r between them, okay, there is a force of gravitation exerted by M1 on M2 of magnitude G M1 M2 divided by r squared. So basically, it says that the force of attraction between any pair of masses anywhere in the universe is proportional to the product of the masses and inversely proportional to the distance, the square of the distance between the two masses, right? So the bigger the masses are, the bigger the forces of attraction are, the bigger the distances are, the smaller. That's what it's saying. So for instance, this is true for any pair of masses in there. So for instance, Omar is attracted to John. Omar is also attracted to Ruby, right? Because they both have masses and there is certain distance between each other. In fact, Ruby is also attracted to John, and John is also attracted by the same amount to Ruby, right? But Omar is probably more attracted to Ruby than he is to John, right? Because a lot closer. Huh? Say that again? It's a thick concept? It's a sitcom. No, however, they might be I'm attracted to every single one of you, but not as much as my attraction to what? There's really one, it's really the Earth, right? That is the most attractive thing here at or near the Earth's surface. Simply because its mass is way, way more than, it doesn't matter how much you ate during the Christmas break, I'm still gonna be more attracted to the Earth, right? So in fact, okay, when we are at or near the Earth's surface, we tend to neglect the gravitational attraction between any pairs of us and focus on our attraction to the Earth, and that's what we call, what do you call that force of attraction that we have? What do we call that? That's the force of attraction. There's a more common term for that. The force of attraction between its weight, it's your weight, right? Because your force of attraction to me is also due to gravity, right? But that amount is negligible compared to the force of attraction between you and the Earth. So if we are at or near the Earth's surface, okay, the mass of the Earth kind of trumps the masses of everything Earth around it. So if we have the Earth here, okay, and let's say here's the center of the Earth, and this is the radius of the Earth, okay, and we have, I'm saying it's near the surface of the Earth, so maybe this is mass M, okay, and let's say that it's not exactly on the surface of the Earth, but at some, what would you call this distance here? H as in height or altitude, maybe, right? How high you are from the surface of the Earth is called what we call altitude, right? So if you look at the Earth and mass M and mass of the Earth is ME, according to the universal law of gravitation, there's a force exerted by the mass on the Earth and also the same magnitude of the force exerted by the Earth on the mass, and that force is going to be what? Proportional to G is what we call the what is G here? There's a special name for it. Is the what? Universal gravitational constant? Is that the name? Does anyone remember the value of that? Yeah, 6.67 times 10 to the that's the 6.67. So here, the force exerted by the Earth on the mass is G, what? Mass of the Earth, right? Mass of the mass divided by, what's the distance between them? R squared, right? And as you can see, if it's not at or near the Earth's surface, it's equal to G M-E. And I'm going to do an algebra. Oh, we're almost done, huh? What time do we end? 35? Okay. So I'm going to do an algebra trick and multiply and divide by RE squared over RE squared. Okay. And I will explain to you why this is so. So the RE squared, the denominator here will become RE squared multiplied by R squared, RE squared over R squared. Why did I introduce that RE squared? What do you notice about this thing? They're all constants, right? Right? Mass of the Earth is constant, radius of the Earth is constant, the universe will, right? So what do you think is the value of that constant? Why is it 9.8? Huh? Okay, he's saying that this is the small g, which is approximately 9. Oh, by the way, it's in physics, it was 9.8. We're better than physics. We'll say it's 9.81 meters per second. Now, why is it that this constant g me over re squared is equal to that small g, 9.81? Because she said somebody told you. What if I told you that's wrong? Are you going to believe me now? That's not necessarily wrong. So what is this G? This small 9.81. This is called the what? It's gravity on Earth. This is really an acceleration, right? This is acceleration due to gravity where? On the surface of the Earth. So this is the acceleration due to gravity on the Earth's surface. Okay, how do I prove that that's true? If I'm exactly on the Earth's surface, what would I do to my mass? How do I get onto the Earth's surface based on the picture? Huh? You said that G, which is 9.81 meters per second squared, is the acceleration due to gravity exactly on the surface of the Earth. Now, I have located my M, right, not on the surface of the Earth. It's actually at an elevation or altitude h. So how do I make my M be located on the surface of the Earth now? I will have to say that its altitude's gotta be 0, right? Which means that if h is 0, generally R, the distance between the centers of mass of the Earth and the center of mass of that particle M, is the sum of R, E, and H, right? Okay? If H is 0, R is now equal to RE, right? So if I substitute that here, this F now, when H is 0, becomes GME over RE squared times M. What happens to this part here? It becomes RE squared over RE squared because R is equal to RE. Yes? Do you understand what I just did? Here's what I did. I want to investigate what's happening at H equals 0. Because H equals 0, the mass is now on the surface of the Earth. But when H equals 0, the R is exactly equal to RE. So I substituted that into this, and that will give me the force exerted by the Earth on my mass when the height of the object is 0. Okay? And this goes to 1, and this becomes GME over RE squared M. And what can you say about the force exerted by the Earth on an object at a height of 0 or exactly at the surface of the Earth? That's what we call the weight of the object, right, on the surface. And what was that equal to in physics? That was m times small g. Yes? So Alan, do you see now why g is that thing? Right? So if I cancel the m's here, this thing here must be equal to g. Okay? So replacing this circle here with a small g is actually advantageous to me because now I can say and express the weight of the object now. So the force exerted by the Earth on the mass at a non-zero h can now be what? Equal to mg, right? Multiplied by RE squared divided by RE plus H quantity squared. Are you okay with this expression now? I replaced R now by RE plus H. Okay, so if you want to find your weight at some altitude H, you just use this. And I don't need to know, as you can see, I don't need to know the exact universal constant of gravitation. I don't need to know the exact mass of the Earth. I don't need to know the exact radius. Oh, I need to know the radius of the Earth, right? But I can find my, as you can see, the higher the H is in the denominator, the smaller your weight's gonna be. So if you want to lose a lot of weight, just go to Mount Everest. Of course, if you climb up Mount Everest, you're really gonna lose a lot of weight. Okay, but as you will see, what's the elevation of Mount Everest? Huh? 7 kilometers. Okay, what's the radius of the Earth? 7 kilometers. Okay, what's the radius of the Earth? 6,371 kilometers. So Mount Everest is 6 divided by 6,000, right? And you square that, that's even going to be a tiny, right? So it's probably not worth flying to Mount Everest to lose that tiny little, you know. Just go to the gym and you lose it without having to. Okay? I think that's all the time we have for now. And then next time we're going to talk about vectors. I don't know. V, how are we doing with time? I don't know. We still have 1 minute. So vectors, okay, we all know what vectors are. Physical quantities can be classified as scalar, A vector, there's actually something beyond a vector. When you get to upper division engineering physics courses, that we will talk about tensors, okay, which are even more complicated than vectors. But for now, a scalar is a quantity that can be represented by a real number. Can someone give me a few examples of this scalar quantity? Speed, okay. Anything else? Numbers. It's really, we're talking about physical quantity, something that represents something in real life. Huh? Displacement. Displacement is not a scalar, it's a vector, because you can move in different directions. Distance, yes, or length, right? Mass, right? Area. What else? Time. On the other hand, a vector is something that needs both magnitude and direction, right? And examples of these are, of course, displacement, right? Velocity, acceleration, what else? The vector of obsession for us in this class. What do you think is the vector of obsession for us? A force. And we represent a vector by an arrow on top of it. Okay. What makes a vector is it's in order to completely identify it, you're going to need not just a magnitude, but a direction. Is temperature scalar or it's scalar, right? It can have plus or minus. Having a plus or a minus doesn't give it a direction, right? It's just a sign, because we know that a real number can be plus or minus. Okay, let's stop here. Next time we're going to review what the sorts of things that you can do with vectors. And then I need to stop recording.